Chapter 15 Mechanism Address Translation. In developing the virtualization of the CPU, we focused on a general mechanism known as Limited Direct Execution or LDE. The idea behind the LDE is simple. For the most part, the left program runs directly on the hardware. However, a certain key points in this, such as when a process issues a system call or a timer interrupt occurs, arrange it so that the OS gets involved and makes sure the right things happen. Thus, the OS with a little hardware support tried best to get out of the way of the running program to deliver an efficient virtualization. However, by interposing at those critical points in time, the OS ensures that it maintains control over the hardware. Efficiency and control together are two of the main goals of any modern operating system. In virtualizing memory, we will pursue a similar strategy, attaining both efficiency and control while providing desired virtualization. Efficiency dictates that we can make use of the hardware support, which at first will be quite rudimentary, for example, just a few registers, but will grow to be a fairly complex, for example, TLBs and page table support, and so forth, and you will see. So control point implies that you always ensure that no application is allowed to access any memory but its own. Thus, to protect the application from one another and always from the applications, we will need help from the hardware here too. Finally, we will need a little more from the VM system in terms of flexibility, but specifically we'd like for programs to be able to use their program space in whatever way they would like, thus making the system easier to program. And thus we arrive at the defined class. The class: how to efficiently and flexible virtualize memory. How can we build an efficient virtualization of memory? How do we provide the flexibility needed by application? How do we maintain control over which memory locations an application can access, and thus ensure that application memory accesses are properly restricted? How we do all over this efficiently. The generic techniques we will use, which you can consider addition to our general approaches of limited direct execution, is something that is referred as a hardware-based address translation, or just address translation for short. With address translation, the hardware transforms each memory address, for example, an instruction fetch, load, or store, changing the virtual address provided by instruction to a physical address where the desired information is actually located. Thus, on each and every memory references, an address translation is performed by the hardware to redirect application memory references to their actual locations in memory. Of course, the hardware alone cannot virtualize memory, as it just provides the low-level mechanism for doing so efficiently. The OS must get involved at a key point to set up the hardware so that the correct translation takes place, and must thus manage memory, keeping track of which locations are free and in use, and judiciously interleaving to maintain the control over how memory is used. Once again, the goal of this work is to create a beautiful illusion. The program has its own private memory, where its own code and data reside. Behind virtual reality lies the ugly physical truth that many programs are actually sharing the memory at the same time. At the CPU and CPUs, it switches between the running one program that the next through the virtualization. The OS, with the hardware help, turn the ugly machine reality into useful and powerful and is to use abstraction. 50.1 Assumptions. Our first attempt to visualizing memory will be very simple, almost laughably so. Go ahead, laugh all you want. Pretty soon it will be the OS laughing at you when you try to understand the ins and outs of the TLBs, multi-level pages tables, and other technical wonders. Don't like the idea of always laughing at you. Well, you may be out of luck then, just how the OS rolls. Specifically, we will assume for now that the user's address space must be placed contiguously in physical memory. We will also assume for the simplicity the size of the address space is not too big and is specifically that it is less than the size of the physical memory. Finally, we will also assume that each address space is exactly the same size. Don't worry if the assumptions sound unrealistic. We will relax them as we go, thus achieving a realistic virtualization. Section 15.2 an example. To understand better what we need to do implement address translation and why we need such a mechanism, let's look at a simple example. Imagine what there is a process whose address space is as indicated in figure 15.1. What we are going to examine here is a short code sequence that loads a value from memory, incremented by 3, and then stores value back into the memory. You can imagine the C language representation of this code might look like this. Okay, tip, the interposition is powerful. The interposition is a generic and powerful technique that is often used to create effect in computer systems. In virtualized memory, the hardware will interpose on each memory access and translate each virtual address issued by a process to physical end address where the desired information is actually stored. However, the general technique of the interposition is much more broadly applicable. Indeed, almost any well-defined interface can be interposed upon to add new functionality or improve some or other aspect of the system. One of the usual benefits of such approach is transparency. The interposition often is done without changing the interface of the client, thus requiring no change to said client. The compiler turns this line of the code into assembly, which might look something like this. x86 assembly use object dump on a Linux or the O2 on a Mac to disassembly. This code snippet is relatively straightforward. It is presumed that the address of the X has been placed in the register EBX and loads the value that the address into general purpose register EAX using the MOVL instruction for long word move. The next instruction adds 3 to the EAX and the final instruction stores the value in EAX back into memory at the same location. In figure 15.1, page 156, observe how both the code and data are laid out in the process address space, and 3 instruction code sequence is located at address 128 in the code section nearly the top, and the value of the variable x address the 15 kilobyte in the stack near the bottom. In the figure, the initial value of the x is 3000 as shown in this location on the stack. When these instructions run from the perspective of the process, the following memory accesses like place. Fetch instruction at address 128. Execute this instruction, load from the address 15 kilobytes. Fetch instruction at address 132. Execute this instruction, no memory reference. Fetch the instruction at address 135. Execute this instruction, store to the address 15 kilobytes. Figure 15.1, a process and this is the address space. This figure 15.2, the physical memory with a single located processes. From the program perspective, each address space starts at the address 0 and grows to the maximum of the 16 kilobytes. All memory reference it generated should be within this bound. However, to virtualize memory, the OS wants to place the process where the else in the physical memory, not necessarily as address 0. Thus, we have the problem how we cannot reallocate this process in memory in a way that is transparent to the process. How can we provide the illusion of the virtual address space starting at 0 when in reality the address space is located at some other physical address? An example of what physical memory might look at once this process address space has been placed in memory is found in figure 15.2. the figure, you can see the OS using the first slot of the physical memory for itself, and it has relocated the process from the example above into the slot starting at the physical memory space 32 kilobytes. The other two slots are also free 16 kilobytes to 32 kilobytes and 48 kilobytes to 64 kilobytes. Section 15.3 Dynamic Hardware-Based Reallocation. To gain some understanding of the hardware-based address translation, we'll first discuss its first incarnation. Introduced in the first time-sharing machines of the late 1950s, is a simple idea referred to a base and bound. The technique is also referred to as a dynamic reallocation. We will see both terms interchangeably. Specifically, we will need two hardware registers with each CPU. One is called base register and other is bound, sometimes called the limit register. This base and bound pair is going to allow us to place the address space whereas we like in physical address and to do, while ensuring that the process can only access its own address space. And in this setup, each program is written and compiled as if it is loaded at this address 0. However, when a program starts running, the OS decides where in physical memory it should be loaded and set the base register to that value. In the example above, the OS decided to load the process at a physical address of 32 kilobytes and thus set the base register to this value. So, aside the software-based reallocation, in the early days, before hardware support arose, some systems performed a crude form of the reallocation purely via software method. This technique is referred to as static reallocation, in which a piece of the software is known as the loader takes an executable that's about to be run and rewrites its addresses to the desired offset in physical memory. For example, it is an instruction was the from the 10,000 into a register, for example, MOVL 10,000 and EXA, and the address of space of a program was loaded starting address 3000 and not 0 at the program thing, and the loader would write instruction to the offset each address by the 3000, for example MOVL 4000, and this way the simple static relocation of the process address space is achieved. However, the static relocation has enormous number of problems. First and most importantly, it does not provide protection, as processes can generate bad addresses and thus illegally access other processes or even OS memory in general. However, support is likely needed for true protection, and another negative is that once placed, it's difficult to later relocate on address spaces to another location. So the interesting things start to happen when the process is running. Not when any memory reference is generated by the process is translated by the processor in the following manner. Each memory reference generated by the processor is a virtual address. The hardware and the content of the base memory to this address, and usually the physical address that can be issued to the memory system. To understand this, let's trace through what happens when a single instruction is executed. Specifically, let's look at the instruction from our earlier sequence. The program counter PC is set to 128 when the hardware needs to be fetched this instruction. It first adds the value to the base register value of 32 kilobytes, 32,768 to get the physical address of 32,896. The hardware then refetches the instruction from that physical address. Next, the processor begins executing the instruction. At some point, the processor then issues the load from virtual address 15 kilobytes, which the processor takes and again adds to the base register 32 kilobytes, getting the final physical address of the 47 kilobyte and thus desired content. Tip: hardware-based dynamic reallocation With dynamic reallocation, a little hardware goes a long way. Namely, a base register is used to transform virtual addresses generated by the program into physical addresses. A bound or limit register ensures that such addresses are within the confines of the address space. Together, they provide a simple and efficient virtualization of memory. The transforming a virtual address into physical address is exactly the technique we refer to as address translation. That is, the hardware takes a virtual address, the processor think it is referencing and transforming it into a physical address, which is where the data actually reside. Because this relocation of the address happens at runtime, and it's because we can move the address space even after the process has started running, the technique is often referred to as dynamic reallocation. Now you might be asking, what happened to the bound limit register? After all, isn't it the base and bound approach? Indeed it is. You might have guessed. The bound register will help too with the protection. Specifically, the processor will first check that the memory reference within the bound to make sure it's legal, and the example above, the bound register would always be set to 16 kilobytes if a processor generates a virtual address that is greater than the or equal to the bound, or one that is negative. The CPU will raise an exception, and the process will likely be terminated. The point of the bound is thus to make sure that all the addresses generated by the process are legal and within the bounds of the process, as you might have guessed. We should note that the base and bound registers and hardware construction kept on the chip, one pair per CPU. Sometimes people can call the part of the process that helps with the address translation in memory management unit, MMU. As we develop a more sophisticated memory management technique, we will be adding more circuitry to the MMU. A small side about the bound register, which can be defined one of the two ways. In one way, as above, it holds the size of the address space, and thus the hardware check the virtual address against it first before adding the base. And the second way, that it holds the physical address of the end of the address space, and thus the hardware first add the base and makes sure the address is within the bound. Both methods are logically equivalent. For simplicity, we will usually assume the former method. The example translation. To understand address translation via base and bound in more detail, let's take an example. Imagine a processor within a unprocessed space size of 4 kilobytes. Yes, unrealistically small, has been loaded in a physical address 16 kilobytes. Here are the result of the number of address translation. The address, virtual address, physical address, and you can see from this example, it is easy for you to simplify to add the base address to the virtual address, which can be viewed as an offset into address space to get the resulting physical address. Only if the virtual address is to be or negative will the result be a fault, causing an exception to be raised. 15.4 hardware support a summary. Let us now summarize the support we need from the hardware. Also see figure 15.3, page 161. First, as discussed in the chapter on the CPU virtualization, we equal to different CPU modes. The OS runs in a privileged mode or a kernel mode, or where it has access to the entire machine. And application runs in a user mode where they are limited in what they can do. A single bit, perhaps stores in some kind of a processor status word, indicate which mode CPU is currently running in, and upon a certain specific occasion, for example, a system call or other kinds of exception will interrupt the CPU switches mode. The hardware must also provide base and bound registered and served. Each CPU does an additional pair of register, a part of the memory management unit (MMU) of the system. When a program is Learning, the hardware will translate the address by adding the base value to the virtual address generated by the user of the program. The hardware must also be able to check whether the address is valid, which is accomplished by using the sound register and some circuitry within the CPU. The hardware should provide special instructions to modify the base and bound registers, allowing the OS to change them when the different processes run. The instructions are privileged only in kernel or privileged mode can be register be modified. Imagine the have a user processor could read and if it could arbitrarily change the base register while aside the data structure, the free list, the OS must track which parts of free memory are not in use so as to be able to allocate memory to processes. Many different data structures can be, of course, be used for such a task. The simplest which will assure here is a free list, which simply is a list of ranges of the physical memory which are not currently in use. Figure 15.3 the dynamic allocation hardware requirements. The learning and limiting it, and they quickly flush such dark thoughts from your mind as they are ghastly stuff of which nightmare are made. Finally, the CPU must be able to generate exceptions in the situation where the user program tried to access memory illegally when the address is out of bound. In this case, the CPU should stop executing the user program and arrange the OS out of bind exception handlers to run. The OS handlers can figure out how to react in this case, likely terminating the process. Similarly, if a user program tries to change the values of the privilege base and bound registers, and the CPU should raise an exception and run those that try to execute the privileged operation while in a user mode handler. This CPU also must provide a method to inform it of the location of the handlers. A few more privileged instructions are thus needed. 15.5 is operating system issues. Just as the hardware provides a new feature to support dynamic reallocation, the OS now have new issues and must handle. The combination of the hardware support and OS management leads to the implementation of the simple virtual memory. Specifically, there are few physical critical junctures where the OS must get involved to implement our base and bound version of the virtual memory. First, the OS take action when a process is created, finding space for each other's space in memory. Fortunately, given our assumption that each other's space is smaller than the size of the physical memory and the same size, it is quite easy for the OS. It can simply view physical memory as an array of slots and track where each one is free or in use. Where a new process is created, the OS will have to search a data structure, often called a free list, to fine-tune for new address space, then mark it used. With variable size address spaces, life is more complicated, but we will leave the concept for future chapters. So figure 14.4, 15.4, dynamic reallocation operating system responsibility. Let's you can an example in figure 15.2, page 157. You can see the OS using the first slot of physical memory for itself, and it has a relocated process from the example of a pointer slot starting at the physical memory address 32 kilobytes. The other two slots are free, 16 to 32 kilobytes, and 80 to 54, 48 to 64. Thus, the free list should consist of these two entries. Second, the OS must do some work when a process is terminated. That is when it is exits class free or is force free, killed because it misbehaved. When it reclaiming all of its memory for use in our processes or the OS. Upon termination of a process, the OS does put its memory back on the free list and cleans up with any associated data structures as need be. Third, the OS must perform a few additional steps when a context switch occurs. There is only one base and a bound register pair on each CPU, so after all, their values differ for each learning program. As each program is loaded in a different physical address in memory, thus the OS must save and restore the base and bound pair when it switches between the processes. Specifically, when the OS decides to stop learning a process, it must save the values of the base and bound register to the memory. In some in some process structure, such as a process structure or process control block (PCB). Similarly, when the OS resumes the learning process or the learning on its first time, it must set the values of base and bounds on the CPU to the correct values for this process. We should note that when a process is stopped that is not running, it's possible for OS to move an address space from location in the memory to another really easily. To move a process address, the address first deschedules the process, then the OS copies the address space from the current location to the new location. Finally, the OS updates the sprite base register in the process structure to point out to the new location. When a process is resumed, its new base register is stored and it begins running again. Obviously, that insertion that the data are now in a completely new spot in memory. Fourthly, the OS must provide exception handlers or a function to be called as discussed above. The OS installed these installers every time via privileged instruction. For example, if a process tries to access to the memory outside its bound, the CPU will raise an exception. The OS must be prepared to take an action when such an exception arises. The common reaction of the OS will be of the hostility. It will likely terminate the offending the process. The OS should be highly proactive. The machine is running and it does not take kindly a process trying to access memory or execute instruction that it shouldn't. But misbehaving process, it's been nice doing you. Figure 15.5 limited direct execution dynamic relocation at boot. Figure 55 and 56, page 164, illustrate much of the hardware OS interaction in a timeline. The first figure shows what the OS does at boot time and to ready the machine for use, and the second shows what happens when a process A starts running. Note that each memory translation is handled by the hardware with no OS intervention. At some point, middle of the second figure, a timer needs to occur, and the OS switches to process B, which executes a bad load, to an illegal memory address. At the point, the OS must get involved, terminating process and cleaning up the by freeing B's memory and removing each entry from the process table. As you can see from the figures, you are still following the best approaches of limited directed execution. In most cases, the OS sets up the hardware appropriately and lets the process run directly on the CPU. It's only when the process misbehaves that the OS has to become involved. Section 15.7 Summary. In this chapter, we have extended the concept of limited directed execution with a specific mechanism used in virtual memory known as the address translation. With address translation, the OS can control each and every memory access from a process, ensuring the accesses to stay within the bounds of the address space. Key to the efficiency of this technique is the hardware support, which performs the translation quickly for each access, turning the virtual addresses, the process view of the memory, into the physical ones, the actual view. All of this is performed in a way that is transparent to the process that has been relocated. The process has no idea is memory references are being translated, making for a wonderful illusion. We have also seen one particular form of the virtualization known as base and bound of dynamic relocation. Base and bound virtualization is quite efficient, as only a little more hardware logic is required to add add a base register to the virtual address and check that the address generated by process is inbound. Base and bound also offer protection. The OS and hardware combine to ensure the process can generate memory references outside its own address space. Protection is certainly one of the most important goals of the OS. Without it, the OS could not control the machine. If processes were free to overwrite memory, they could easily do nasty things like overwrite the trap table and take over the system. Unfortunately, the simple technique of dynamic relocation does have its inefficiencies. For example, as you can see in the figure 15.2, page 157, the located processes of using the physical memory from the 32 kilobytes to 48 kilobytes. However, because of process stack and the heap are not too big, all of the space between the two is simply wasted. This type of the waste is usually called internal fragmentation, as the space inside the located unit is not allowed or used, that is fragmented and thus wasted. In our current approach, although there might be enough physical memory for more processes, we are currently restricted to replacing an address space in fixed size slot, and the internal fragmentation can arise. Thus, we are going to need more sophisticated machinery to try to better utilize physical memory and avoid internal fragmentation. On our first attempt will be a slight generalization of base and bounds, known as segmentation, which we will discuss next time. Okay, references and homework simulation.